The Weenie formula, an extension of Einstein's field equations. Visible matter in the universe accounts for approximately 5% of the total mass-energy density. This discrepancy between observable matter and gravitational effects is not speculation, but a measurable fact. The Weenie formula addresses this problem through a systematic extension of Einstein's field equations. Einstein's general relativity describes gravity as curvature of four-dimensional space-time. The field equations establish a direct relationship between the energy-momentum tensor, which describes the distribution of matter and energy, and the Einstein tensor, which quantifies geometric curvature. This theory works excellently in the realm of classical gravitational phenomena, but fails to explain several cosmological observations. Galaxy rotation curves show a clear deviation from predictions based on visible mass. The outer regions rotate at nearly constant velocity instead of the expected decrease proportional to the square root of distance. These flat rotation curves require either additional mass or a modification of gravitational theory. The Weenie formula pursues a hybrid approach. The mathematical core of the Weenie formula extends the Einstein-Hilbert action with additional scalar fields. These fields represent compactified dimensions in the sense of Kaluza-Klein theory. Each scalar field phi I contributes its own energy-momentum tensor, which adds to the right side of the field equations. The result is a modified field equation containing additional degrees of freedom. Dark matter is not treated as a separate particle species in this formalism, but as an emergent phenomenon of the additional dimensions. The scalar fields couple gravitationally to ordinary matter and generate effective additional terms that behave phenomenologically like dark matter. The crucial difference lies in predictability. While dark matter models require free parameters for density and distribution, these emerge in the Weenie formula from the dynamics of the scalar fields. The accelerated expansion of the universe, confirmed by supernova observations and cosmic microwave background radiation measurements, requires a positive cosmological constant or a dynamic field with negative pressure. The Weenie formula implements both, a constant lambda term plus a variable potential V of the scalar fields. This potential can be time-dependent, enabling dynamic dark energy, whose equation of state evolves over cosmological timescales. Quantum fluctuations of the vacuum also contribute to the energy-momentum tensor. In quantum field theory, the vacuum is not an empty state, but the ground state with minimal energy. This zero-point energy diverges in naive calculations, representing the cosmological constant problem. The Weenie formula regularizes these divergences through the additional dimensions, which act as a natural cutoff. Experimental verification of the Weenie formula occurs on multiple levels. Gravitational wave detectors like LIGO and Virgo could measure deviations from general relativity predictions. The additional scalar fields modify the dispersion relation of gravitational waves and lead to frequency-dependent propagation velocity. Precision measurements of arrival times of gravitational wave signals from different frequency bands could detect these effects. On galactic scales, the Weenie formula predicts specific correlations between the distribution of visible matter and effective dark matter profiles. These differ from predictions of conventional cold dark matter models. In particular, the cusp core problem, the discrepancy between simulated and observed density profiles in galaxy centers, could be resolved through the modified dynamics. The compactification of additional dimensions determines their phenomenological effects. With a compactification radius in the range of the Planck length, effects on macroscopic scales remain minimal. Larger radii would lead to measurable deviations from Newtonian gravity on sub-millimeter scales. Torsion balance experiments already set strict limits for such modifications. The theoretical consistency of the Weenie formula requires further investigation. The renormalizability of the theory is not guaranteed, and the stability of vacuum solutions must be analyzed. Negative eigenvalues in the scalar field propagator would lead to tachyons and make the theory unstable. The coupling constants must be chosen so that all physical modes have positive energies. The weenie formula represents a concrete proposal to address several open problems in cosmology and gravitational physics within a unified framework. It makes testable predictions and thus differs from purely speculative approaches. The coming years will show whether experimental data support or refute this extension of Einstein's theory. Regardless of the outcome, the mathematical structure of the weenie formula expands our understanding of possible gravitational theories and their consequences for cosmology.